This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, welcome for another lecture of construction history. With this one we'll talk about concrete, and we will focus about concrete during the 20th century, particularly in Australia. I will focus only on some aspects of this very vast topic. Now, concrete obviously had an enormous influence during the 20th century, both from a point of view of the technological development of construction methods, but also from a cultural point of view. Concrete arguably has influenced to a great extent the development of the modern movement in Europe, and then from Europe to the rest of the world. So this is by all means not a comprehensive outline given the immensity of this topic. So we will focus on some aspects that I believe I've contributed to the adoption of concrete in Australia at large scale. So we're not talking just about architecture here, we're also talking about engineering and how somehow an entire industry has pinned itself on this material. Probably from the early 1900s, certainly also after World War II to a great extent. The majority of the focus today will probably be more in between the two wars, so between World War I and World War II, but we will also go beyond the Second World War and see how some of these topics have followed up. Now, concrete is not only a matter of interest for Australia. Modern concrete technology, from a point of view of construction, that it's actually not a topic that it's quite well addressed, I would say, today in research. Certainly in Australia, arguably overseas, there has been much more studies that have focused on this. But let me start with this quote from an architect who was a European architect of Jewish origin, who was active in Germany during the 1920s, who in that period went to visit North America. And the architect in question is Eric Mendelsohn. And Eric Mendelsohn went to Buffalo, the state of New York in the US, to observe close by a new building topology that became very important for the Midwest, but for the development of America's infrastructure. And this topology was the grain elevator, or the silos for the wheat silos. And when Mendelssohn came to New York, he said these words. He said, we're confronted by the purity and the sheer size of these concrete structures. He was in awe and wrote back to his wife in Europe, saying that there was this incredible sense of space consciousness of these volumes of concrete that they were also surrounded by a chaos of loading and unloading of corn from and to railways to ships, etc. So crane monsters with live gestures, it says, orders of silo cells in concrete, stone and glazed brick, etc. So there's this very romantic view of concrete that emerged in the 1920s, particularly in Europe, but certainly looking at countries like America. And I will show you here how this audacity in creating new nation, new world using concrete wasn't just an American phenomenon, but it was also something that came here to Australia. Yes, with a lot of influences from America, as we saw before. We saw how the Americans influenced to a great deal the Australians also for steel, and so did the British as well. But so Australia becomes this territory where both, perhaps the best of both worlds, we would like to think, but not necessarily so all the times, was adopted in order to create a new nation on a modern basis. So one of the silos that Mendel saw in Buffalo was very much something like this, except that this wheat silos are not in the state of New York, but they were actually built in Sydney in the 1930s. So not far from the times in which Mendelssohn was inspired and then brought back this vision back to Europe. This in particular is the terminal of a system of grain elevators, as they are known in the United States, and by extension have been also defined as such here in Australia. Grain elevators are silos that contain wheat, and they are a part of a network that is connected by railroads and that stores wheat from several farming stations, and then from these stations is distributed to terminal centres, usually in ports. In this case, in Sydney, is the Whites Bay Grain Elevator Terminal. In parallel to this sort of rhetoric of the grain elevator, which wasn't just a rhetoric so much in Australia, but seemed to be more of a European fascination for it. In the same years, and particularly from the very late 1800s, Australia also started to build very large dams. And this was quite a unique exercise, certainly new for Australia. But it was also one of the most important episodes or series of projects that forced Australians to become familiar with concrete. This is the Beetaloo Dam, probably one of the earliest, if not probably the very first very large project that also had some echoes in worldwide for its size. Built in the 1890s, actually just in 1890 to be precise, and it is a dam that is its function is a reservoir, so for provision of water, and it was built obviously using concrete and using a technique that at the time was known as the arch dam. So it's an arch-shaped dam that withstand obviously the pressure of the reservoir from the opposite side of this great picture. And you can see here obviously how the construction of the dam requires very ingenious methods of handling of the material. So you can see here there's a bucket here of concrete suspended from a wire and a system of pulleys and wheels that moves along this stretched wire. This is also known as a flying fox. So the concrete obviously was mixed here on the side, and then it was transposed along this wire, and it was poured from this keyboard, so this reverse bucket along obviously the profile of the dam. Now this is another dam built in the same period in the Barossa Valley, this time in South Australia still, like the one before. And in this picture you can observe not only the workers here almost at the very top of the structure. You can obviously observe the sheer size of this structure, but you can see how the formwork is being installed as a series of soldiers or posts that are used to frame and form the arch of the dam. And these soldiers are bolted directly onto the concrete below. So it's a traditional system of formwork using timber, but that is able to be moved vertically, so assemble and disassemble continuously to create this curvature. What is interesting about this early experiments is that Australia had the labour at least to build these ones, although labour was certainly in great demand in Australia. But the concrete in itself was often mixed using cement that came from overseas. So there was a shipping usually of very large quantities of concrete that came from overseas, most of the times from Britain, sometimes from the United States. And then the concrete was obviously mixed, adding water and local aggregates. But the cement, which was the most precious material, was imported still in these days from overseas. And of course, again, this is another dam in Tasmania this time, the Great Lake Dam in Maina. We're now a bit later in the 1920s, but you can see how the problem of handling in this case has been resolved by having this moving concrete plant that has been set up specifically for the job on the territory, and then you have these hoppers here that obviously distributes and the concrete from this movable plant onto the areas where it is needed. And this is the dam under construction, and you can see this is a different typology of dam. It's a series of multiple arches, sort of side by side, that have been used to withstand the force of the water. Now, a dam works on the principle that in section, a dam would be something that has to support, typically, obviously, prevent water to go on one side of a particular creek, but the problem of a dam is that the water pressure, the hydrostatic pressure, increases at the bottom of the structure. So normally dams have a tapered profile in section where the base of a dam is much thicker, and the top can reduce itself to not to nothing, but certainly to a much thinner profile. In addition to this, in plan, a dam that can be used to work like an arch if it's shaped in this way, so to contain the basin, and we're familiar now with the principle of the arch, where an arch can basically work in compression in virtue of its shape. So often there is this combination of the taper profile and the arch itself. You can observe here how the methods of formwork used are still traditional formworks. They would have been quite difficult to control in this case, because you're still relying on a set out of timber members that have to be transposed. In this particular project, actually, they had some troubles because the timber was not very well seasoned. So some of these problems with dams obviously induced the industry to develop new techniques. Now, this is a dam that it's one of the largest in Australia. We're now moving towards the 1940s. It was completed also after World War II in the 50s. But this is a dam that probably shows how eventually this technology, this very large infrastructure ability, was mastered. And apart from the problems of formwork, building dams also means has allowed the Australian industry to learn a lot about concrete. So one of the biggest problems in dams is that given the sheer volume of concrete involved, the process of hydration of concrete with cement can generate some heat, and this is a normal phenomenon of any process of hydration for any concrete. But when the volume of concrete is like it is required for dams, this heat can be significant, and it can generate cracks in the structure. It can create problems. So this is one of the dams that somehow bypass this problem by having a series of modules or shells that are, rather than being completely solid, it's a series of horizontal and vertical plates that have been assembled together. A much more convenient system also, because it economizes the materials instead of being just an entire full mass of concrete. In this case, is a structure that is resisting through its gravity, by the fact that it's really heavy, but it is doing so with some sort of means of efficiency. And you can see obviously here it's a much more sophisticated concrete working system here, where you have engineered formwork systems that are not far from the ones we have today. But in these years also, these are also the years where Australians learned to understand the problems of heat generation during concrete construction, and therefore the application, the creation of admixtures like early, low heat, for example, cement that was actually invented also by some Australians during these years. And this is the same dam now being completed. So you can see the shells, this sort of stepped structure. It's then being completed by a slipped form external skein that is tapered, and that completes the entire dam, the Warragamba Dam in New South Wales. So again, this is the point where we see the maturity of the Australian industry. And again, another beautiful dam here in Tasmania, the Gordon River, where we have here a combination of the skills that we saw in the previous example, but here we see it also applied to a dam that is a double curvature. So this is the side where eventually the water will reach its top, and you can see here there is an arched curve approach to the problem of hydrostatic pressure, but there's a double curvature, so there's an arch running in this direction as well as also working in the opposite direction. You can notice up here there's a concrete plant again set up on purpose for the job, and a series of cranes that obviously help to handle construction here. You can see slip forms here, systems of formwork that are automatic and are able to lift themselves up by reusing the structure built below, etc. So this is now the 1970s. But there's another typology of infrastructure that is really important for the diffusion of concrete in Australia, and that is the grain elevator. Now, Australia, as you know, is a country that is rich of wheat farms, or at least it used to be, and in particular, an area of the country that is facing inland from the eastern coast, the so-called wheat belt. There's a stretch of land that is suitable for farming wheat that has been used historically in Australia from the 1900s. Like other countries in the world, like Canada, the Midwest in North America, but also some countries in South America, and the large production of wheat combined with very large expanses of land created problems of handling of this production. And so during the late 1800s in America, but especially in the first part of the 20th century, many countries, and in the Americas in particular, in Canada and United States, developed this idea of rationalizing the production of wheat by storing it in terminals, in towns, in country towns, and then connecting all these stations together with railways, and then eventually dispatch this production of wheat more conveniently to large centers like cities. Like, for example, in the Midwest, eventually everything conveyed back to Chicago, and then thanks to the river system from Chicago to the Midwest, then the wheat was able to be sold and dispatched also to other urban centers. Now, this process also happened in Australia, and first in New South Wales, dispatching the grain to Sydney and Newcastle, and then eventually also in Victoria, where the grain would be eventually conveyed to a terminal in Geelong. And so this was the traditional wheat handling method of the past, where wheat was put into Utah sacks. So as you can imagine, very, very inconvenient, very much exposed to rot and risk of loss of product, etc. So the system, instead of storing wheat inside terminal silos, became obviously a natural evolution that was married with the fact that you could have a railway system that allowed the product to be distributed. And concrete becomes the ideal material to contain wheat, because wheat, believe it or not, when it is stored in very quantities, can have a lot of dust, and dust can also self-ignite itself and cause fire. So some of the first silos for containing wheat were actually often timber, eventually steel, but steel was also problematic for other reasons, and eventually when fire happened inside these silos or grain elevators, all the effort of concentrating the production somehow caused even more damage. So concrete, being a fireproof material, became the ideal complement to this method of handling of food. And let's not forget that. So these are not buildings for people, but they're buildings for containing food product in this case. And you can see here in section how there's a series of beans, as they are known, which are the silos themselves. They're all stacked in a series, in an array. And there is a system here of lifting machinery, the elevator itself, that basically receives the wheat product, and there is a series of buckets that load the product up. Then there is a distribution silo here that eventually will take it to a conveyor belt along this line here, from which the grain is then sorted according to its quality. Depending whether the grain is of a certain type, of a certain quality, it can be distributed to a specific bin. When the grain then is needed to be redistributed, the bin is releases the grain at the bottom again to another conveyor belt that sort of brings it back to this side of the grain elevator system. Again, the grain will travel up again to some extent, and then from here it's conveyed back to an area for loading, which could be connected to a railroad or a drive-through for trucks, etc. So you can see this sort of management where all the production can be rationalized and distributed. And the material that surrounds this is concrete. Now, there's something very important about this. This is not just concrete building, but it's concrete building that is cylindrical. And yes, it's the kind of concrete that inspired people like Le Corbusier and others in Europe to adopt this sort of idea of the purity of forms of modernism, etc., at least to some extent. But it is also important because this is concrete that is suddenly becoming a presence also in the countryside. So Australia built hundreds of these silos, America probably thousands, and so did other countries in the world. So this is the point where suddenly concrete becomes part of the Australian landscape as well, not only in an urban setting but also outside of cities. And the technology that allows this is also a very clever method of construction, which is known as slip forming. So slip forming is a way of extruding concrete, in this case in a cylindrical shape, by using a formwork that moves and that is not continuously assembled and reassembled like we saw in some of those dams, these early dams we saw before. Slip forming, it's a system that is self-climbing in a certain sense. So it has shutters, it has a series of rods that are embedded inside the concrete, and there's a series of jacks that allow to move the shutters inch by inch or slowly as they progress. And so once the concrete hardens, progressively the shutters move vertically and more concrete is poured inside them. Then that concrete hardens and the slipform are able to keep traveling. They travel along some rods that are then embedded inside the concrete. They're not the reinforcement rods, but they're left lost in the construction once the slipform proceeds vertically. Now you can see here an example of this procedure. This is not a silo; it's a television antenna building actually in here on the right, under construction in the early 50s in America. But the picture is very interesting because it shows closely how these formworks are operated. You can see there is a series of bars, and there's this sort of reverse U-shaped structure, which is known as a yoke. And this is the rod that is embedded inside the concrete. You can see it's sort of buried in there. This is the fresh concrete. The two shutters here on the side, and this is a jack lever that is hand operated, so that by twisting it, by turning it, the yokes will push upwards, and with them the whole shuttering system will proceed. You can see there's a worker here, there's another one there. So in this case, multiple workers will be coordinated their effort to lift up the shutters simultaneously. Obviously, there is a science behind. The concrete has to harden. There is a certain rhythm, a certain performance that has to be achieved. The advantage of this system is that the formwork can be reused and reassembled, but the inconvenience of it is obviously the fact that once the work starts, they have to be completed. So there's very little capacity for stop and starting. It can be done, but generally speaking, a slipform structure, you want to start it and finish it. Sometimes even without stopping at all and going for a 24-hour cycle. Now, this is a patent that illustrates, for example, how the system all comes together. Now, you can recognize these yokes we described before. You see these rods that eventually will become part of the structure below. You can see the shutters, and you can see here the concrete that is already hardened, that is used to support the formwork. And then, of course, there's a decking here, a platform from which it is possible to work. You can see here again this jacking system, the lever, very similar to the system we just saw before, which was an American system. This is an Australian patent of the 1930s. It's almost identical to what we saw before. And then this technology becomes the means through which we invade the Australian country with these structures. Very utilitarian structures that in time also became obsolete and often superseded by other systems, but the obsolete destiny is often because of larger problems of production, perhaps not necessarily because of the failure of these structures not to perform. Some of these structures are still used today. They were certainly used to a great extent for a period of time. In Victoria, there was two typologies of these silos known as the Geelong type or the Williamstown type. The Williamstown is this one you see here in the picture, and this is an example where you have two bins side by side. This is a typical country station. It's not a terminal, where you have slip-form structures going up. You can observe here the platform clearly recognizable by the characteristic yokes and lifting rods of the system, and this is the structure completed on the right. Another example, again, some close-up, you can observe clearly how these are built using the slip form, and you can recognize the slip form sort of character also by the structure itself. You can almost see how this is extruded continuously. There's all these lines here that sort of reveal the sort of horizontal progressive extrusion of the concrete. Now, what is interesting is slip forming started with slip forms, with silos or grain elevators, but after World War II, this technology became also sort of interesting and used in the construction of multi-story buildings. Yes, it also became the technology that is slip forming that was used, and it is still used today in high-rise structures worldwide, and it originated from wheat silos also in America. So there is a continuity and a crossover and technology transfer. In this case, there is of global significance and relevance. And one of the first examples of slip form structures in Australia was this apartment block in Neutral Bay near Sydney, where an entire structure was, or an entire apartment building of 7 floors was slip formed in a matter of days. I think it was, by memory, 5 or 6 days. So obviously the advantage here is the speed of construction. And these apartments were built by a company known as Concrete Silos, just to obviously to reinforce the idea of this technology transfer. These are not cylindrical shape, but it's a slip form that has been adapted to rectangular shape. And it is a slip form system that uses mechanical and hydraulic jacking systems. So with this technology, there's a spin-off that happened in the 1950s, which is the so-called lift slab, which again uses this idea of having forms, in this case, and a system of construction that can move vertically, But rather than extruding concrete vertically, the lift-up slab methodology uses some hydraulic jacks, which you can observe here in this picture below, mounted on some columns of steel sometimes, or concrete later on. And these columns can be used to drive vertically a series of slabs. So a slab is poured face down, and then eventually it can be elevated along these posts that are operated by some hydraulic jacks. The hydraulic jacks hold the slab from the underside, and once the slab is poured, it's lifted up to a next level. So the construction usually stacks a series of slabs that are separated from one to another, and then all these slabs are eventually progressively lifted up until you obtain, you can see here the steps of the sequence where you go from a series of slabs all stacked together, and then progressively the slabs are pushed vertically and separated using these hydraulic jacks that grab them from below, drive them through some vertical rods and put them in the right position. And this is an example here, still standing, I believe, in St Kilda along Beach Road, and a building, a residential building. It's quite noticeable. If you drive along Beach Road, you probably see it quite easily. And the building is using clearly a lift slab form here. You can see they're celebrating at the top. They completed the structure. You can see these columns of steel that have been used to guide these slabs that have been first poured face down and then lifted up using hydraulic jacks. So this is another example in here on the right at St Leonard in New South Wales, again near Sydney, where you have some posts here of concrete, some pillars of concrete, and then these slabs here that are first poured here and then jacked vertically, believe it or not, to their final position up. So the construction starts below, and then one floor, second floor, and then more floors will come until the whole building is proceeding from top down, using again a technology that is hydraulic jacks and self-climbing. The hydraulic jacks were also the ones that eventually will substitute in the slip forms the hand-operated jacks that we saw before. Now, another important thing to understand about concrete in this period is we saw mostly, obviously large-scale projects, but we also spoke about systems, and they are very often proprietary. Another important thing, and this is an example, if you like, of some of these systems, is this is the so-called BRC, or British Reinforced Concrete System, that gained some popularity in Australia in the early phases of concrete. And these systems, as we know, in the early stages of concrete development, were often in the hands of proprietary ownership and patents, etc. Some of the systems continue. New systems came along, particularly those mechanized which we just saw. But by the time we reach the early 1900s, concrete starts to become more of a standard rather than a system, a proprietary system method of construction. Now you can recognize here how this company in particular is still advertising itself as a system that has obviously all the solutions, foundations, beams, intersections between columns and beams, etc. And as you know, there's also other systems that became quite popular in Australia, like the mushroom collar systems, like the Turner system. But some of these systems eventually start to become more they start to diffuse themselves in Australia beyond the initial patented system, and start to lead to new systems that they've somehow modified or reintroduced and continue to add more proprietary knowledge onto the previous ones. This is the one example of this system that combines the mushroom column approach, which we saw for the Turner system that was of American origin. Here you can see that the mushroom system is being used in combination with a ribbed slab, where the infill between the ribs of concrete is now this time terracotta, so the same terracotta we already discussed previously, as the complement of steel for fireproofing purposes, now reappears here as lost formwork. And so the terracotta now meets with concrete and to some extent also displaces steel in some applications, and by combining two materials that are both equally resistant to fire. You can see here an example from a company, the Liverpool Tile and Terracotta Company, or LTC, Liverpool Terracotta System, based in Sydney in this case. And you can see how the products that they advertise is showcased here. Also, with steel as well as in combination with concrete. So you can see here an example here of the application of the LTC system, where you have terracotta tiles, structural tiles. Particularly look at this here in section, where you have the tiles and then you have a concrete structure that has been used to infill in between the tiles. So the tiles will be set up in the same system we saw before, like in steel, and then reinforcement will be put in between two tiles, and one tile in this case will be also inserted on the underside, so there's a homogeneity of underside, and then concrete is poured on top with a reinforcing grip mesh. So you can see here the arrangement also in plan, etc. And then you can see here how concrete can also be used to embed steel, and this is an important development that we'll come back when we discuss a bit later on in the impact of concrete also in high-rise construction in Australia. You can see here a system where you have both steel and concrete combined together, where you have steel embedded in concrete and then terracotta tiles and then reinforcing bars in between. And now terracotta tiles were not the only means to achieve this system, but also sometimes we have products that were gypsum blocks like these ones, Victor gypsum blocks, that you can see them here installed. And you can see them again using the same principle, in this case in combination with mushroom head columns, which are illustrated also in this picture. And you can see clearly the gypsum blocks here acting as lost formwork and this ribbed surface. Then eventually plaster will be applied on top, and you can see obviously how in this case here they show a mushroom column, but they also show an alternative. There's no capitals, as they call them, required. So this also opens up the idea that you can have structures that are not necessarily octagonal or pyramidal in their head, but much more simplified. And these systems could be used both in a one-way or a two-way arrangement, as you can see here. So again, concrete beams, columns, sometimes steel beams embedded in concrete, and then tiles of gypsum, or sometimes concrete blocks, which also appear in this period of time. They appear here in Australia. They also start to become popular beyond Australia. There's some examples in New Zealand that can be observed at the same time. And so the combination of concrete here with this lightweight terracotta gypsum or concrete itself start to reinforce the idea that you can use concrete successfully also for commercial floor construction, and therefore for multi-story construction. Now, not everything went smoothly when concrete started. In 1925 in Melbourne, multi-story concrete structure, not so tall, 6-7 floors, collapsed and killing 4 people. And it collapsed as a result of poor mixing, basically. So poorly applied quantities of cement and water. Excess of water in particular weakened the structure, and lack of cement and the right amount of aggregate caused a partial collapse of the building, killing some people. So this episode, as well as others, sort of induced the industry to reconsider some things. One was the practice of mixing concrete on site. Now, concrete on site was inevitably exposed to imperfections and lack of reliability. Now, with a combination of availability of automotive transport in these years, you start to observe an exponential growth of a new method of concrete delivery, which is known as ready mix. Now, ready mix was a company set up in England that eventually became a worldwide network of the concrete industry. Ready mix fundamentally was a system where a concrete plant could produce concrete off-site in a factory-controlled environment where the consistency of the product could be ordered specifically for the project. The quality of the mix will be in good hands, and then the concrete will be loaded into a truck and delivered on site just on time. Well, it's exactly what we still do today. You can see here one of the first early ready-mix trucks in action in Sydney in the 1930s. Ready-mix started as an idea in America in the 1920s, 26 to be exact. But so Australia picked up this quite quickly, and by the time this happened, so this potential to deliver concrete on site from a manufacturing plant where the quality of the mix can be controlled, well, this also went along with the development of standards. Standards as we know them today, as an industry accepted practice that guarantees a minimum benchmarks for quality. And you can see here, this is a publication from the 1930s, where you can observe something that you'll be familiar with already, a slump test for concrete that is exactly like the same one we still use today. So ready mix, slump tests, and the ability to control the quality of concrete along more secure and safe and well-engineered mixes. It's what starts to somehow disengage concrete from the dominion of these specialist contractors that also had proprietary limitations on it. And then concrete and its ability to combine itself with other materials, as we saw, whether gypsum or whether even steel to much extent. And so suddenly concrete, by being a peripheral product itself, it becomes a new main product of the construction industry, and itself generates peripheral products that become a complement. For example, a whole range of waterproofing products. The list will be long, but I just mentioned and I illustrate here the example of non-porite. Non-porite was a range of products that they were used to seal or waterproof concrete. So concrete suddenly becomes a new center, a new trade on its own right that has sub-trades and other affiliated activities. And another important development of this year is also the idea that you can produce concrete not necessarily on site all the time. Once the idea of mixing also from on site is removed, there's also the understanding and the intuition that you can also cast off-site concrete itself and produce some prefabricated element, which we normally refer as precast concrete. Now, Victoria was at the forefront of this. In the 1930s, we have several systems, or a couple of systems actually, one of which is known as the Fowler system, which was the most successful. That was here, it's illustrated. You can see a panel of an entire wall with some window openings in these locations, with some casements and a doorway here. And again, more windows with the casements already installed. You can see how here the panel has been possibly, very likely, poured flat and then it's lifted up, so it's tilted up, and then eventually it will be transported on site or moved to a more convenient site and assembled together with other panels, and then in this case most likely receiving a column to tighten the structure. So there's this other approach to construction that suddenly takes concrete from an on-site experience to a combination of industrial production, products, integration of other systems, and of course always, all the time, the ability to then finish the product on site. Now we saw dams, we saw grain elevators, but of course there's also there could be many more examples we could show here for bridge construction. Out of the many that would be significant in Australia, but also overseas, imagine the work of important engineering figures like Maillard in Switzerland and many others. Well, out of those examples here, I'll show one that is important perhaps for Australia, the Gladesville Bridge in Sydney. Now, the bridges of Sydney are mostly known. You think about obviously the Iron Bridge of the Sydney Harbour, but there's another remarkable bridge in Sydney. It is this one, a 300-meter arch of concrete, precast concrete, put together with a series of hollow shells, and then this arch spanning not less than 300 meters, 304 meters to be exact, and this arch is then used to support a deck here for a road that crosses the bay. Now you can see here in the background, of course, you know, the Sydney Harbour Bridge, but you can see here the Gladesville Bridge, also equally prominent for the city. So the arch is composed of a series of hollow precast elements that have been sort of put together using this temporary false work driven directly at the bottom of the bay there, and then a series of piers have been erected along the extrados of this arch to receive the road and the deck. And you can see here how the arch is built very much like a voussoir, like an old traditional arch, where you see a series of elements all put together. And in this case, they were also post-tensioned. So once the arches are put together, they're tensioned to give them some additional stressing during construction, horizontally as well as along the length of the arch. So there is all these voussoirs that are first installed, supported temporarily. You can see the platforms here below, and then eventually post-tensioning is applied to put some additional stress that keeps all these voussoirs of very large precast elements all together. Now, precast also becomes the ideal solution for not only for large bridges like what we saw, but for many buildings like this one. The state government offices here in Melbourne, and you can see here how this idea is being used almost to the extreme, when you have 3 floors here of a building that has been all entirely prefabricated and lifted up in very large and tall section, and then propped temporarily. Then eventually a structure will come to infill with the floors. The same technique was used at the state government offices also for the construction of the tower. You can see here in this case a column several floors high being craned and dropped in position. And of course then this idea of precast, sleeve forming, and the ability, why not, to complete construction works on site creates it gives enough variation and enough opportunities to use concrete in many applications, including for the construction of skyscrapers. So you can see here, for example, Collins Place under construction. You have a slip form core, same technique of silos, but this time using hydraulic jacks, not manual lever jacks. So the same hydraulic jacks of the lift up slabs. You have precast envelopes and a combination of steel and concrete to complete the floors. So all these techniques developed in obviously not in a space of 50 minutes like what I just said, but it took some time. They're not necessarily all techniques that were specific for Australia. They were in fact very much of part of a global diffusion of techniques. They were not necessarily also a bed of roses or a continuous evolution of innovation and of triumph of technology, but sometimes they sort of evolved in different times and with some trials and errors. The lift-up slabs were not all the success and that they looked like. They actually somehow didn't quite take off as they did. Some techniques like slip forming eventually will be superseded in the 70s by jump forming that we use today. But all these techniques somehow reinforce the importance nonetheless of concrete as a material that combined mechanization and a material that also was the perfect outcome for an industrialization of the concrete industry. And of course this was picked up also by culturally by designers. So you can see, for example, here, this is a photograph from Max Dupain in the 1930s, and you can see how clearly he's deliberately juxtaposing, you know, the forward-looking image of these concrete silos. We're talking about the 1930s here, the industrialization of food production, and then you see a car, of course, inside a car, and from the rear view mirror you see a brick structure. So it's a very well crafted picture is telling you we're looking forward, and the past of brick and masonry construction is left behind, superseded by this new material, concrete. Is, yes, compressive most of all, compressive strength like masonry, but it is the product of industrial revolution that finally has reached this maturity. And you can see also how architects somehow started to develop craft out of this technique. There's a whole board marking generation of projects in Australia, but also elsewhere, that he understands the expressive potential of concrete as a material that is almost able to be crafted by leaving marks of the construction process. And so this is not only an aesthetics, but it's also an aesthetic that implies that you must know and control the construction process. So board marking, like in this example of a building from Taglieti, it's a system that has to understand the formwork. It implies that there is a memory of whatever happened on site that has been projected and left permanently on the face of the structure. And remarkably, Australia is one of probably the earliest and most significant examples of board marking. Long before brutalism, there's a building at the University of Western Australia, Winthrop Hall, where an architect from Melbourne, Rodney Oslop, who was possibly inspired from some examples from overseas, created this very nice portico using board-marked concrete to create a simplified Doric column system with some barrow vault kind of archways. Certainly not a modern-looking building by appearance, but modern in its intent of using concrete as a way to somehow reveal a stratification of the construction process. And then, of course, there's more to come. There's the idea that you can use concrete also for its plastic potential. In this case, the mushroom columns that we saw before in the Turner or some of the Innesbell systems evolve, and they evolve in a system that is not proprietary anymore. It's bespoke in the South Lawn car park of our university, where you can go and observe this remarkable structure where you have mushroom columns here that have been used to receive a tree, for example, from the lawn on top, and to also then receive drainage. So the abilities of concrete also to be formed along curved structures become an instrument of design in the hands of engineers when you're talking about shell construction system like at the Academy of Science in Canberra, but also an element of sculptural ability when they're integrated in a facade, and in this case as a sunshade system at the Perth Council House. And of course, also concrete becomes the ultimate material that allows the Sydney Opera House to exist as a material outcome. And in this case, it's concrete. Yes, it is curved concrete. But it is concrete also that is precast and prefabricated. And of course, then we have some leftover all this culture that still remain in the country, but we're not necessarily understanding all the time what the implications of these materials. So we also have an heritage of concrete that is problematic, where we have often a misunderstanding of its value, whether it's because it's underrated or whether it's because simply it is what it is. It's a material that it's quite brutal in a certain sense. It's a material that is a direct product of the construction process, and when left exposed, very often we still don't appreciate it. This is probably why we have now a series of silos of the leftovers of the grain elevators that we discussed before, which were an object of industrialization in the country. It's probably by no mistake that Australians feel like they have to somehow rectify this look by putting some graffiti on them. So now I'm not necessarily criticizing or accepting either way, but I just like to use this as a way to consider that any construction system that we inherit from the past is not simply a matter of techniques and technologies, but also has some cultural implications that can be understood in virtue of these techniques, but also cultural implications that go beyond those techniques. So I'll leave you with this one, and this will conclude to some extent the discussion on concrete, at least for this week. But there'll be some more to come in the next one. So keep looking at the LMS, and I'll see you later.